Hi everyone, so let's continue our discussion on combination circuits. So in the previous video I told you that we are going to study some standard circuits now, but before standard circuit let's take one more video where we don't discuss any standard circuit but just some normal circuits. So here as well you do not need to mug up any final expression. So in this video whatever that we are dealing, you do not mug up any final expression. Okay, so first one is code converter, then we will see 7 segment display, and then we will see parity generator and parity checker. So these three kind of circuits we are going to see, and you do not need to remember the final answer. Okay, so first, this is the first question. You can do it on your own. Design a 4-bit binary to gray code converter. You need to convert binary to gray. So basically you can, if you need to draw the block diagram, where I will draw the block diagram. So let's just say this is my combination circuit. My input is 4-bit binary and my output should be 4-bit binary. I will make in this manner only. My input is 4-bit binary. My output will be gray code. Certainly it will be 4-bit only, because in binary and gray code number of bits would be the same. So if this is my input 0000, so with respect to that what is the gray code? 0000 only. If this is my input, with respect to that what is the gray code? This is the gray code. For 2 what is the gray code? This is the gray code. How I have written gray code? 8 times 0, 8 times 1. 4 times 0, 4 times 1, 4 times 1, 4 times 0, 2 times 0, 2 times 1, 2 times 1, 2 times 0, 2 times 0, 2 times 1. So I hope you must have built the habit now. Okay. Now for each line, for each this G3, G2, G1 and G0, we just need to denote this G3, G2, G1 and G0 in terms of B3, B2, B1 and B0. So let's talk about G3. In G3 you can directly see that G3 is directly equals to B3. So I do not need to make any K-map. G3 is directly equals to B3, right? What about G2? What are the min terms of G2? Min terms of G2 are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 4, 5, 6, 7, 8, 9, 10, 11. So these are the min terms. So just put them in your what do we say it? K-map. 4, 5, 6, 7, 8, 9, 10, 11. Now what I need to do? I just need to minimize it, and directly I can see this is a quad and this is another quad. So these two are the quads. So this quad is B3 B2 bar plus B3 bar B2, that is equals to B3 XOR B2. So similarly what did you get? G3 you get is B3 XOR B2. In the same manner what you will get as G1, you can do it on your own. Try doing it on your own, because we have seen a lot of example. You can do it on your own and you will get it as B2 XOR B1. And what you will get as G0? G0 you will get as B1 XOR B0. You can see. Let's talk about G0. So that would be 0 XOR 0, 0 XOR 1, 1 XOR 0, 1 XOR 1, 0 XOR 0, 0 XOR 1, 1 XOR 0, 1 XOR 0, 1. Yeah. Now let's just say in the examination this question is coming and they are asking you to derive this expression. So will you derive it there, or you already know? You already know it, right? Because we know the conversion. If I am going from binary to gray, BG, if I am BG I will never look down. So B3 goes as it is. I am never looking down. So this XOR this, B2 XOR B3, then this XOR this, B1 XOR B2, and then this XOR this, B0 XOR B1. So this is your G3, this is your G2, this is your G1 and this is your G0. So I directly remember it. I am not going to derive it in the examination by making the K-maps. If they are asking me the expression, then I will just directly write I am going from B to G. Okay, in that manner I will write that's it. Okay, so this is the final expression. Sorry, this is G2, this is G1. Right? Let's write gray to binary code converter. Gray to binary, GB. If you are ganda bacha, you will look down. So this is G3 will come as it is. Now in the next time what will happen? G3 XOR G2. Next what will happen? G3 XOR G2 XOR G1. And now next what will happen? Next what will happen is that G3 XOR G2 XOR G1 XOR G0. So I could have done it with the I could have done it with the truth table as well, but I am not doing it because I already know the answer. I remember the answer. So simply this will be your B3, this will be your B2, this will be your B1, and this will be your B0. So you can directly write B3 is equals to G3, B2 is equals to G3 XOR G2, B1 is equals to G3 G2 XOR G1, and B0 is equals to all XOR. So in that manner, no matter how many bits are given, I can always write binary to gray code converter and gray to binary code converter, because I already know by the trick. If you are BG, that means you will never look down. If you are GB, if you are Ganda Bacha, that means you will always look down. So looking down, and this bit will always be equal. So G3 looking down, G2. Okay. Let's go to the next question. This is BCD to XS3 converter. So this is a bit interesting topic. So you need to convert BCD to XS3. You can write both of the codes. BCD code would be, and 4-bit, only in 4-bit, okay. 4-bit BCD to 4-bit XS3. We can take any number of bits, 8 bits, 12 bits, 16 bits, but we are taking 4 bits only. So 0 will be, in XS3 it will be 3, 1 will be 4, 2 will be 5. Here this is 4, 7, 5, 8, 6, 9, and this is 6, 9, and 7, 10, 8, 11, and this is your 9, 12. What about this bit? 1, 0, 1, 0. Next is 10. If my input is 1, 0, 1, 0, what would be my output? Don't care. Say yes or no. Why don't care? Why it is don't care? Because 1, 0, 1, 0 is never occur. 1, 0, 1, 0 will never occur. At the input 1, 0, 1, 0 till 1, 1, 1, 1 will never occur. Why it will never occur? Because I told you these are unused bits in BCD. Unused bits in BCD. So these are unused bits. Are you getting this point? So all these are don't care. So if I write the expression of x3, then what is this min term? This is 5. So 5, 6, 7, 8, 9. Now all these are don't care. 10, 11, 12, 13, 14, 15. Because how can you write 14 in BCD? In BCD you will write 14 as this. And 4. 4 is 0, 1, 0. So you cannot write 14 in 4 bits. So these will go as don't care. So 14 cannot be written in BCD code using 4 bits only. It would require 8 bits. So it will not come in this part. So all these goes as don't care. So what do I see here? If I this octet I can see, then any octet? No. This quad and another quad. Okay. If I write here, this is 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. So in this quad, all these are changing. Only one thing is constant, that is B3 plus. This was about octet. In quad, what is constant? B3 bar into B0 plus. In this one, what is constant? B2 into B1. Here what is constant? B2 is constant into, in this one, B1 is constant. So this is the expression of x3. I used the don't care so that I could make a quad. If you hadn't tried these don't care, then it would be a problem for you, right? Because you would be making this pair there, and it would give more, it would give the expression with more literal count. But we need the minimized expression. Then we know that rest of the part will go to don't care. So that's why we are putting don't care here, and this is the expression of x3. Try deriving x2, x1 and x0 on your own. Okay, do it on your own. So I will only do for x2, then you can do for x0 is directly you can see x0 is b0 bar. x0 is b0 bar, you can directly see here. For x1 you can do it on your own. For x2 I will do it. So what all are the minterms for x2? For x2 what all are the minterms? 1, 2, 3, 4. 1, 2, 3, 4. 5, 6, 7, 8, 9. And plus don't cares are also there. Don't cares are there. 10, 11, 12, 13, 14, 15. Okay. So 1, 2, 3, 4, 9. 1, 2, 3, 4, 9. Don't get starting from 10. 10, 11, 12, 13, 14 and 15. Okay. This looks interesting now. Can we get anything out of it? Let's write 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. So I guess this can be a pair only. But I can get two quads here. What all are those two quads? This quad I can see, right? I cannot make any octet. This quad I can see, and another quad I can see. There you go. Okay. So if I write the expression for this one, so here which all are constant? b1 bar, b0 bar, b2. b1 bar, b0 bar, b2. If I talk about this one, then b2 bar is constant and b0 is constant. b2 bar, b0. And what about this one? Here b1 is constant, and what about this row? So b1 is constant, and what about these? b1 is constant and b2 bar is constant. b1, b2 bar. So that's the expression we are getting for x2. Similarly, x3, x0 we can directly see. This you can do on your own. So on your own. Okay. Do the practice on your own. You will get this expression, right? Which is actually an XOR gate. So this will look very simple. Okay, then let's move to the next one. Now, like some people would be thinking, sir, that how they will ask these kind of question in the examination. This would take a lot of time. So they can ask the output expression of a particular bit. That what will be the output expression of x2. So in this way they can ask the question. The way I have expression, the way I have asked here. So a 4-bit binary code, b2, b1, b0, b2, sorry, b3, b2, b1, b0 has been converted into BCD code. So BCD code is of 8 bits. Why is that so? Because in binary you can represent 10 in how many bits? In binary you can represent 10 in 4 bits only, like 1 0 1 0. But for BCD you would require 8 bits. That would be 0 0 0 1, and for 0 it would be 0 0 0 0. 11 you can easily denote, right? 8 to 11. But here you would require 2 bits. That would be 11. That this would also be 1. So this is 1 and this is 1. So that's the thing. That's why they have given 8 bits. So make the truth table on your own and tell me the expression of C2. Now let's see the solution. So in the examination, if I need to talk about only C2, so I will write down the truth table of C2 only. Like this is my 0. So 0 0 will be converted to 0. This is my 1. How 1 will be converted? Let's write one more. So 1 will be, these bits will be 0 only, and 1 will be, this is 1. Because 1 can be written as 0 1. So this is 0 and this is 1. What about 2? So 2 will be written as this. Rest all bits are 0. But I need to talk about C2 only. So I will think about C2 only. What about 3? In 3 as well C2 will be 0 because this will be 3. What about 4? In 4 this will be 1. Rest all will be 0. These all also will be 0. What about 5? 1 0 1. What about 6? 1 1 0. What about 7? 1 1 1. What about 8? What about 8? So this would be 1 there and this would be 0. In 8 this would be 1, right? 8421 code it is, 8421. This also has the value of 8421. Okay, so this will be 8. What about 9? In 9 as well, this will be 0. In 9 as well, this will be 0. Let's write down in the same manner only. This is your 9. So in 9 as well, this will be 0. What about 10? 10. 10 means this is 10. So 10 means this would be 1 and this would also be, this would be 0. What about 11? 11 means this would be 1 and this would be also 1. What about 12? So this would be 1 and this would be 2. In 2, what do you write? In this manner you write. So this is 1 and this is 2. Here 13, this is 1 and this would be 3. 14, this would be 1 and this would be 4. And what about 15? This would be 1 and this would be 5. So that's all are the minterms. So what are the minterms of C2? So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So these are the minterms of C2. 4, 5, or in the examination, like I would think, okay, what would be 0, 0, 0? So I can directly write down the minterms, no, in the examination. I will not make this table. If I need to only think about C2, so in the examination, what I would be doing, that I will write A3, A2. In the rough work, I will write this thing first, C3, C2, C1 and C0. Then I would know that I need to think about this. So I will start from 0. If 0, 0, 0 is there, this will be 0. If 1 is there, this will also be 0. If 2 is there, this will also be 0. If 3 is there, this will also be 0. If 4 is there, this bit will be 1. So I will write 4. Then if 5 is there, this bit will be 1. If 6 is there, this bit will be 1. If 7 is there, this bit is 1. If 8 is there, this bit will be 0. 9 is there, this bit will be 0. 10 is there, this bit will again be 0. 11 is there, again 0. 12 is there, again 0. Then 13 is there, again 0. Then 14, 15, it would be there. So directly in the examination, I can write down this expression. In the mind only I can think. I do not need to make all these 0, 0, 0, 0 and 0. I can directly write down my minterms. So these minterms, if I know, then I can directly make my K-map. So that's how you will be solving in the examination, and these kind of questions can be asked because people will spend a lot of time in making all these kind of things. But we need to think there intelligently. Okay. So 4, 5, 6, 7, 14, 15. 4, 5, 6, 7, 14, 15. Right? Yeah. So very easily we can see this is a quad here. I can use a different color. This is a quad here and this is a quad here. So 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. C2. C2 is what? B3 bar B2 plus. What about this one? So here B1 is constant, right? And what is constant? B1. And what about this? Here B2 is constant. So that's the final expression. And this one B2 is constant, here B1 is constant. So B1, B2, and what about this? Here B3 bar B2 is constant. So that's the final expression of C2. So in that manner only they can ask the expression of C1 as well, C0 as well, C3 as well, anything they can ask in the examination. Okay, and I hope you would be comfortable. There will be nothing like don't cares because they are giving 8 bits now. If they are given 4 bits, then there would be don't cares. But here they have given 8 bits, so now I can represent all the numbers in 8 bits. Okay. Now let's study about 7 segment display. So code converters you should be comfortable now. Like very easy problems, just whatever that is given, just convert that to the another code and write down the final expression. Okay, I hope code converters you are comfortable. Let's see 7 segment display, very easy topic. So you might have seen this display in calculator. You see this display. Let's just say you write down 7, not in scientific calculator, in a normal calculator that commerce guy uses. So if you write down 7, so how it will be written? In this manner, right? If you write down 1, if you click on 1, this will be written. If you click on 2, this is how it will be written. Oh, sorry. Actually, this would be 1 only. These will be 1. Okay. I mean, all this is how it would be done. This is how it would be written. If you write down 5, this is how it would be written. This would be 5. So why it is called 7 segment display? Because there are 7 segments. 1, 2, 3, 4, 5, 6, and 7. So there are 7 segments. So let's just see some examples. These are the examples only. Again, let's see it. How will 0 be written? 0 will be written in this manner. How will 1 be written? In this manner. How will 2 be written? 3 will be written in this manner. 4 in this manner. 5, right? You can make it on your own. 6, 7, 8, 9, right? So these all are the numbers. Now let's see the question on this, because like there is no concept, a simple problem, and only one question has been asked in GATE examination, so that you will solve on your own, or I can see that in assignment. Okay, because I do not want you to show, like there is only one question available. So this question I took from my side, and one question will be there from GATE PYQ, so that I will pick in the assignment. Okay, we will see that in assignments. That would be very easy. You can solve it on your own as well. So let's just see this problem. Design a circuit that detects the number that uses lower left segment in 7 segment display for a 4-bit BCD code input. So our input is BCD code. So always in combination circuit, always we need to see, first thing is what is our input. So input is our BCD code. So it can go from 0 to 9. This is our input BCD code, B3, or I have written ABCD. Okay, ABCD I have written. So I will write down by ABCD. ABCD. Now let's just say there is some random input. This is our combination circuit. Okay, and it will give a single bit output. That is our Y. Okay, yeah, Y. So let's just say my input is 0, 0, 0, 1. What is the decimal equivalent of that? 1. So what will happen? 1 can be written in this form. So is it using lower left segment? No, this is using D and E only. What is lower left segment? This is lower left segment. So lower left segment is C. So if you are making 1, is it using C? No. So the output will be 0. Now let's just say this is my input. This is my input. So what is the decimal equivalent of this? 3. If you are making 3, this is how you will make 3. So is it using your lower left? Again it is not using. Output will again be 0. If this is your input, then what is the decimal equivalent? 2. So are you using lower left one? Yes, then output will be 1. This is what you need to design. That's it. Input is a BCD code. You convert that to decimal. It will detect that number only which uses the lower left segment of the display. Okay. So what is my input? It could be 0, 0, 0, 0, right? If it is 0, 0, 0, 0, that means decimal equivalent is, you should do it on your own first. Decimal equivalent is 0. Is it using? No. If my input is 0, 0, 0, 1, oh sorry, it is using, it is using lower segment, it is using, so it would be 1. For if my input is 0, 0, 0, 1, that means this is the scene, not using. For 2 it will use, for 3 it will not use, for 4 it will also not use, for 5 you can think on your own, it will not use, for 6 yes it will use, for 7 it will not use, for 8 it will use, for 9 it will not use. Now what about these? They don't care, right? Look, these are the possible combinations known, like ABCD can be 1, 0, 1, 0 as well. But what will BCD say? That these are don't care for me, right? Because these are unused bits. These are unused combinations. Here we write all the possible combination of ABCD, which are all these 16 combination. But these combination are unused for me. If these are unused for me, BCD will say these are unused for me, then I will give my output as don't care. Because I don't care, whatever the input is there, output will be don't care, right? So now let's Let's check back again that if I have written it correct. 0 it will use, 2 it will not use, 3 sorry 0 1 2 it will use, 3 it will not use, 4 it will not use, 5 it will not use, 6 it will use, 7 not use, 8 use, 9 not used, and then all these are don't care. It's not that you will write 10. Now 4-bit input is there, so all these are don't care. 4-bit BCD. Okay, so what all are the minterms? Minterms are 0 1 2 3 4 5 6 7 7 wouldn't be there, 8 wouldn't be there, 9 will also not be there, right? And don't cares are 10 11 till 15. So in the examination directly I can write down these minterms, right? So first I will think 0 will not use, 1 will not use, 0 will use, 1 will not use, 2 will use, 3 will not use, 4 will not use, 5 will not use, 6 will use, so 6 I will return, 7 will not use, 8 will use, so 8 I will write, 9 will not use, so 9 I will not write, so 0 2 6 8. So directly I can write down the minterms, right? And rest all are the don't care. So 0 2 6 8 9 10 11 12 13 14 and 15. So what do I see here? All look, without using don't care I can see a quad here, 1 2 3 and 4, and then directly this. Look, in temptation what would be the first step? That let's make a octet, but that is of no use. I can directly pick this one. All these this one is already taken, so directly I can see if I make this one, no, then what is the scene? What would be the scene? If I take this, then there would be three like there would be three terms. If I, let's just say if I had taken this and then this quad and then this I would have taken, because this one will not be used. So I have to use this one. So I would have to take 1, 2 and these 3, but this is not required at all. This is not required at all. So directly a 4 and then a quad, right? Basically this octet is redundant. There is no use of this. This octet is redundant. All these ones are being in the box. These are in the box only. So all the ones are in the box. So 0 0 0 1 1 1 1 0 0 0 0 1 1 1 1 0. So you will get the expression C bar D bar plus B bar D bar. So that's the final answer. Okay, we can check here as well. Why I have written B3 B2 B1 A B C D. We always start from here, A B C D. So in this one what do you see? Only D bar is constant, so D bar into B bar, and in this one C D bar, so C D bar plus B bar into D bar. So that should be the final answer, and I hope you are able to do it on your own. So that's it about our this 7 segment display. One more problem will be there, which will be in the assignment, not in this particular class. Okay, let's see the next one. Parity generator and parity checker. So it is used in DGCOM. Okay, in digital communication we will again study about it. It is used in digital communication. Okay, we will certainly study about it again in digital communication. So what do we do? Look, at the receiver I sent this data line. The data line is 1011. If you remember what is data line, in our first lecture we have studied it. What is data line? So 1011 I have sent. At the receiver I should have expected 1011 only, but because of the addition of noise you are receiving 1111. So there is an error. There is certainly an error. So now what will parity bit do? Parity bit will only tell that there is an error. Where there is an error, that it will not tell that there is an error in this bit or in this bit. Parity bit will only tell that there is an error. So what parity defines? So parity simply defines the number of ones. Parity simply defines number of ones. You just need to remember this line. Parity simply defines number of ones it has nothing to do with the number of zeros. A lot of time people get confused that it will tell something about number of zeros. It has nothing to do with the number of zeros. Parity is an extra bit with the transmitted signal that tells about the number of ones. Okay, so it will only tell about the number of ones. So what we will do actually in our circuit. So this is what we will do in our circuit actually. But let's see the two definition. Then we will see what we will actually do. How do we transmit the data? So what do you mean by even parity? Even parity means it will make the number of ones equal to even. So if this is my data line, so what parity I will send? I want to make number of ones equals to even. So I will send 1 because I need number of ones to be even. So here there are odd number of ones. So parity bit would be 1. Here what would be the parity bit? I need total number of ones to be even. So parity bit would be 0. So already these are even, so parity would be 0. Odd parity, it will make the number of ones odd. It will make number of ones odd. Here there are even number of ones. So to make odd number of ones, I will put one more 1 here. And here there are odd number of ones already, so parity bit will be 0. So what we will be doing? So this is a parity generator, okay? This is a parity generator. Let's just say this is a even parity generator. And first we will see here, let's just say this is my input. This is my input. And this is even parity generator I have checked. That means I want to send even number of ones to the parity checker. I want to send even number of, this is at the transmitter side. This is at the transmitter side. And parity checker will be at receiver side. Okay. This will be at receiver side. This will be there at receiver side. This is the transmitter side. This is the receiver side. So this is a even parity generator. That means it will make sure that this parity generator will make sure that at the parity checker you have even number of bits. So if this is my input, then what will be this value? That would be 1. So this is even parity generator. So it would be 1 0 1 0 0. This is my input. Now what is this? This is even parity checker. So what it will check? That the number of ones should be even. At the input side, this is the even parity checker. This was the generator, this is the checker. So what it will do? It will check if the number of ones are even. Yes, if the number of ones are even, it will give error 0. That there is no error. Are you getting this point? What we are doing in parity generator and checker. So first we will see the data line. If we want to generate even number of ones, at the receiver we want to get even number of ones. That means we will generate a parity which will check if the number of ones are even. If it is not even, it will make itself 1 and this will be transmitted to the receiver. At the receiver we will have even parity checker. That means it will make sure that number of inputs should be even. If the number of inputs are even, then it will give error equals to 0. And let's just say if this was odd parity checker. If it was odd parity checker. So what it will see? The number of ones should be odd. If it is odd parity checker, the number of ones should be odd. So if what it will see? The number of ones are even, that means there is an error. So it will throw an error. Are you getting this point? And now let's assume if this was odd parity generator. If this was odd parity generator and this was the input only. If it was odd parity generator, that means it needs number of ones to be equals to odd. So number of ones here are odd only. So parity will be 0. Parity will be 0. And now if this is odd parity checker only, so it will make sure that at my input number of ones should be even. Sorry, number of ones should be odd because it is odd parity checker. So here number of ones are odd only, and if these are odd, it will throw an error equals to 0. And if this was even parity checker, if this was even parity checker, that means it will make sure that at my input number of ones should be even, and if it sees number of ones are odd, then it will throw the error as 1. So this is what we do in transmitter and receiver. I hope this is crystal clear to you. If it is not clear, then you can again watch it, because a lot of people get confused in parity generator and checker. So simple thing is, whatever the checker, whatever generator and checker are there, their task is to make sure that number of ones are even for even parity generator and even parity checker, and it should be odd for odd parity generator and odd parity checker. That's it. This is their task. Okay, in that manner only we will study. So let's see 2-bit even parity generator. So this is my input, this is my even parity generator. What would be your parity? even parity generator. So the task is number of ones should be even. Here what is the number of ones? Number of ones. I am writing one more thing. Number of ones. Here number of ones are 0. That means it is an even number only. So parity will be 0. Here number of ones are 1. It is a, this is even number. This is a odd number. So you see the data line 0 and 1. You got to know that there are number of ones are odd. So I will be 1 so that the number of ones become even. Parity bit will become 1 so that number of ones become even. Here also you will see that number of ones are odd. And in the next one number of ones are even. So in this one what will parity bit do? That parity bit will see that the number of ones are already even, so I will be 0 only. And here it will see that the number of ones are odd, so I will be 1. So what is P? P is D naught XOR D1. Now tell me one thing, in the examination do you actually need to write this truth table? Can you think intuitively? Without writing the truth table, can you think intuitively? What you need to think, that I have an even parity generator and my input are D naught and D1. My parity bit will be 1 if the number of inputs are odd. What I would say, parity bit P will be 1. Listen to this line very carefully. If number of ones are odd, because if odd number of ones are there, then it would be 1, right? Because if odd number of ones are there, it would make it even, so it would be 1, right? That means it is a odd number of ones detector. Odd number of ones detector. And what is odd number of ones detector? XOR gate. So it has nothing to do with the zeros. So if you remember, what was XOR gate? Odd number of ones detector. Odd number of ones detector. And what was XNOR gate? XNOR gate was even number of zeros detector. Even number of zeros detector. But your parity bit has nothing to do with the 0, right? Your parity bit has nothing to do with the 0. So when I am thinking about parity generator or checker, I will never think about XNOR gate. I will always think about XOR gate. Say yes or no? Because your parity bit has nothing to do with the number of zeros. It has everything to do with the number of ones. So I will always think in the manner of 1. And if I am thinking in the manner of 1, that means I will be thinking of XOR gate. Say yes or no, right? So what else you can write? If okay, odd number of ones detector, that means if number of ones are odd, then output will be 1. If number of ones are even, then output will be 0. If number of ones are even, let's just say if number of ones are even, then what will be the output? 1 XOR 1 0, 0 XOR 1 1, 1 XOR 1 0. So output will be 0. And if number of ones are odd, then output will be 1. So this is what we mean, right? Array. Why did I remove it? Yeah. What about this odd parity generator? Odd parity generator. Number of ones should be odd. Number of ones should be odd. So here number of ones are 0, here 1, here 1 and here 2. So here number of ones are even. Here these are odd. These are odd. And this is an even number. So this will be 1. This will be 0 because already these are odd. And this will also be 1. Because here number of ones are even, so it makes sure that it would be odd. Here number of ones are odd only, so it makes sure that it would be odd only. Here number of ones are even, so it makes sure that it becomes odd. Okay. So what is P now? P is D naught XOR D1 bar, which can be written as D naught XNOR D1. Okay. So this is your P. How you will think in the examination? This is my odd parity generator. First you will say, okay, this is an odd parity generator. That means I need to make sure that the number of ones should be odd. So if number of ones at the input is odd, then parity bit will be 0. Number of ones is odd, that means parity bit will be 0. So it is the bar of XOR gate. Because what is XOR gate? You never need to think in terms of XNOR. I told you this thing. Never think in terms of XNOR. Always you need to think in terms of XOR. So what you will think? That I need to make sure that my number of ones are odd. If my number of ones are odd, that means output will be 0. So it is the negation of odd number of ones detector. Say yes or no. Negation of odd number of ones detector. So you will write XOR gate and put negation there. In the end, I will tell you very simple trick. You will be able to write down all the expression. But till now, we are building our concept. So let's go and do the same thing for 2-bit even parity checker. Okay, yeah. This is even parity checker now. So this will be called 2-bit even parity checker only, where 2 bits are data bits and 1 is the parity bit. So you will not say that, sir, this is 3-bit parity checker. No. 2 data bit and 1 parity bit. So what is this? Even parity checker. Even parity checker. So it will see if the number of ones are even, then I will be 0. So here number of ones are 0 only. Here number of ones are 1. Here also number of ones are 1. Here number of ones are 2. Here 1. Here 2. Here 2 and here 3. This is number of ones. So here number of ones are even. So error will be 0. Here number of ones are odd. So error will be 1. Error will be 1. Error will be 0. Error will be 1. Error will be 0. 0. Here number of ones are. So that's the thing. Now what do you think? What is the truth table for this? This is also XOR gate only. Right? You can see 1 is there, 0 XOR 0 XOR 1. 0 XOR 1 XOR 0. 0 XOR 1 XOR 1 is equals to 0. So this is also XOR gate. Now why it is XOR gate? So how you will think? Even parity checker. In the examination, how will you think? If there is even parity checker, that means if the number of ones are odd, then error bit will be 1. If number of ones are odd, then error bit will be 1, because the job of this is to generate even parity. That means it needs to make sure that the number of inputs, the number of ones input should be even. But if the number of inputs are odd, then error will be 1. So this is odd number of ones detector, which is XOR gate only. So even parity checker is a XOR gate only, right? So let's do the same thing for 2-bit odd parity checker. In the examination, how will you think? So if the number of ones are odd, then my error will be 0. If number of ones are odd, then error will be 0. This is odd parity checker. So if number of ones are odd, error will be 0. That means it is the negation of odd number of ones detector. That means it is the negation of this. Can I write down this as this? No, absolutely not. Why so? Because for 3 bits, XOR and XNOR are equal. So I can write down it in this manner. And then there is whole bar. And another expression, more expressions are there, which I have already told you. Camera ko kya ho gaya yaar? Yeah. So more expressions are there. I told you, if one plus sign needs to be converted to dot, then what will happen? 1 bar will go. So if 1 bar goes, then it would be denote even. More expression could be there, which we have already seen in our basic logic gate course, right? And what about this? This is equals to our P dot denote dot D1. Okay, so these are equal. Now odd parity checker it is. So number of ones are even, so it would be 1. Number of ones are odd, 0. Number of ones are odd, number of ones are even. Number of ones are odd, number of ones are even. Number of, so basically opposite of that, right? Number of ones are even, so 1, and number of ones are odd, so 0. So this is the truth table, but we will not derive that table in the examination. We will think smartly. So 3-bit even parity generator. Write down the final expression of the parity. 3-bit even parity generator. How will you think in the examination? 3-bit even parity generator. that the number of ones should be even. Number of ones, if number of ones, let's think in the form of odd. If number of ones are odd, that means output should be 1. If number of ones are odd, output will be 1 because this is an even parity generator. If let's just say there are 3 1, then output will be 1. So number of ones are odd, output will be 1. That means this is odd number of ones detector. So what is that? XOR gate. So what will be your parity bit? That would be A XOR B XOR C. What about this? 3-bit odd parity generator. If number of ones are odd, if number of ones are odd, that means output will be 0. What does that mean? Negation of XOR gate, right? Negation of XOR gate. So negation of XOR gate, which can be written as this, or there are other expression as well, which is this or this. Anything can be asked in the examination. Or so this traveled here, this traveled here. Yeah, more expression that basically this dot can travel anywhere. Okay. 3-bit even parity checker. If the number of ones at the input side are odd, if the number of ones are odd, then error will be 1. Then that means it is odd number of ones detector. If number of inputs are 1, then error will be 1. If number of ones are odd, then error will be 1 because it is even parity checker. It needs the number of inputs should be even, but if the number of inputs are odd, that means it will give output as 1. So this is again XOR gate, which is equals to, again we can write this is equals to this as well, and this is equals to this. And what about this 3-bit odd parity checker? You can do it on your own. It will be just the negation of the previous one. So you can see here, for even parity generator and checker, always XOR gate is used, and for odd parity generator and checker, always the negation of XOR gate is used. So I will not say XNOR gate is used, negation of XOR gate, because sometimes these two can be equal as well, XNOR and XOR. So I will say negation of XOR is used, right? So for n bit, we can write it down: A XOR B XOR C XOR D. In that manner it will keep on going. And for odd parity generator, I will not write dot here, I will write in this manner, okay, and then I will take a bar. What about this? And here for odd it will be the bar. So I will say, do not mug up, but understand the concept. Okay, you should know the concept as well. Now in the examination, any kind of questions can be asked, and in that manner you will be able to solve. What is the job of even parity generator? That number of ones should be even. So if at the input side number of ones are odd, even parity generator will be 1. What is the job of odd parity generator? That number of ones at the in the data line should be odd. If the number of ones are even, or you can say if the number of ones are odd, then output will be 0. That means it is the negation of XOR gate. What is the job of even parity checker? So at the input side, along with the parity bit, so here I should have written parity bit as well, because there will be parity bit. Even parity checker, that means basically 3-bit even parity checker is there. So wait a second, this is a blunder from my side. Even parity checker it is. So there will be 3 bits and a parity bit, no? 3 bit and a parity bit. So here you take like this, and this can be written as A XNOR B XNOR. This is actually even parity. I will again explain it. This was even parity checker. So at the input side there will be 4 bits. No, 3 is the data line bit and 1 is the parity bit. And now combining all those 4 bits, if the number of ones are even, then output will be 0. And if the number of ones are odd, then output will be 1 for parity checker. If the number of ones are odd, that means there is an error, so output will be 1. Got this point? So there will be four kind of input. And here there will be an input, and this also I should write. So in n bit even parity checker, no matter how many bits are there, it doesn't actually matter that how many bits are there. The job is just to make sure that number of ones should be even or odd. So what is the job of n bit even parity checker? No matter how many bits of input are there, the only job is at the input side the number of ones should be even. If the number of ones are odd, error will be 1. So if the number of ones are odd, error will be 1. That means it is an XOR gate, and the next one is simply the complement of that. So that's it about our parity checker and generator. If there is any problem on that, no, there is no problem, there is no issue about this particular lecture. So we have covered everything in a very detailed and short manner so that we could do all the questions correct if these kind of questions are asked. Okay, so these kind of code converter, 7 segment display, and these kind of this what do we say, parity generator and checker, we have studied it, right? In the next video we will study about magnitude comparator, which is also a very easy topic. And if that video is not that large, let's just say that video is of roughly around 30-40 minutes, then I will try to add up that video in this video only, because this is also not a very large topic. Magnitude comparator is also a very small topic only. So let's see it in the next video. Okay, thank you very much.